Okay, go full screen. Okay, so as I told you earlier that um, this is basically week 2's assignment, which I had not solved completely in the last week's tutorial, because I solved one for you, like this one. The first part I solved for the first function, and then I left the other two for you to solve by yourself, so that you can submit the assignment by doing most part of it by yourself. And then I also discussed how this I think this kind of a formula, this kind of a problem where the entropy function is given like this expression, how that should be done. I also gave a hint on that. And one second. Okay, so basically we briefly discussed some parts, but today I plan to first solve the assignment to you, so that even some of you may have solved the entire assignment completely in your last submission date, but I would like you to review again and check if everything is consistent. And then the remaining time, the remaining hour of the 1 or half an hour of the class, I'll give you and provide you some hints on the next week's assignment. And then again, I'll not solve totally all of that by myself, and in the next class we'll again discuss. Okay, so now, so let us begin with our first problem here. So this was said in the problem that we have been given a odd function, even function, which is like fx equal to f of minus x. And then there is a theorem that is already stated here. This is this theorem, where you can see that in the left hand side there is a limit and a summation, and on the right hand side you have simply an integral expression. And all you have to do is that you have been given different choices of the function fx, which is obviously an even function, given the fact that is stated that the function has to be an even function. And similar three functions are given, and all of these three cases you have to just not only check that LHS equal to RHS is really true, but also you have to also get the value, that what is this value of this integral, or what is the value of the left hand side limit. And that is the possible answer that is given in one of these four options, right? Now the first function was the thing that I think was a bit non-trivial, I'd say, not difficult, but a bit non-trivial for you to solve. But I already solved that for you in the last class. So you basically needed to use a function structure called digamma function, which is somewhat related to the gamma function. I defined that function and showed the entire solution to you in the class number 2. So after that, I think the next two functions are not very complicated. I would rather say it is very simple in comparison. So even so, I'd like to, for the sake of completion, I'd like to finish the solution completely for you. So let's say this is our class 3, and we are solving week 2 assignment. So if at any point you have some doubt on any solution that I am doing currently, so you can stop me and ask me. I will try to answer. Okay, so this is our question number 1 and part number 2. So the function that is given here was fx equal to e to the power of minus mod x by a. First of all, you can check for yourself that it is all one second. Okay. So all of you can please mute yourselves, unless you want to ask some questions, so that there is no extra noise. Right, thanks. So basically, let us first check for ourselves that it is basically an even function, because if you put f of minus x here, you would see that it is minus of minus mod x by a. Just replace x by minus x. But basically the minus sign is also in between the mod. sign, right? So it will just absorb the minus sign and again give you back the same expression. So it is same as f of x. So we see that f of minus x equal to f of x. So definitely the function given to you is an even function. So that is checked. So if f of x is an even function, then the theorem that is given after that will be valid for this structure of f of x. So what is the theorem? So the theorem that is stated here is, so it is that limit of, just let me check what was the theorem. Limit of lambda tends to 0, then lambda sum over n equals from 1 to infinity function of lambda n equal to, right hand side there is an integral half minus infinity to plus infinity, then I think it was fx dx. Okay, so this we need to prove that LHS equal to RHS. This theorem becomes valid even if we use this formula of f of x. So let us start with the left hand side limit. So LHS. What is LHS? LHS, just let me directly put the function's value here. So limit lambda tends to 0, then lambda n equals from 1 to infinity f of lambda n, and that is equal to limit lambda tends to 0, lambda n from 1 to infinity, and then you simply put lambda n in place of x in the form of f of x. So we'll just write e to the power of minus mod of lambda n by a, right? Now because here you see that we have been using this lambda, it is nowhere mentioned that lambda will be negative or whatever, and n is also going from 1 to infinity. So you can instead of putting the mod sign everywhere, you can just simplify things and write this just as e to the power of minus lambda n by a, assuming that this will be positive, because mod of some function will always give you a positive value. Okay, so based on that, we'll just now what we'll do is just expand this exponential e to the power of minus lambda by a. So lambda, and then because there is a summation over here, right, in over n from 1 to infinity, so we'll use different values of n starting from 1. So it is e to the power minus lambda by a plus e to the power of minus 2 lambda by a plus e to the power of minus 3 lambda by a, and like that it goes to infinity because your n value is, upper limit is infinity. Now if you just simplify things a bit, you will see a connection that just take e to the power of minus lambda by a common in this case. So what you are left with is this series 1 plus this sum e to the power of minus lambda by a plus e to the power of minus 2 lambda by a, and again this goes to infinity. Now what is the need of doing this? Because you clearly see there is a pattern in this summation, because before this you saw that there was no particular thing that you could make out of this part, but here once you have taken out e to the power of minus lambda by a, the remaining sum is a known formula of the sum. You know the what will be the value of sum. It is a infinite series sum. Okay, infinite series sum, where we know that if infinite series goes like this, that 1 plus x squared plus x cube plus up to infinity, then this series sum give you 1 by 1 minus x. Okay, so this is the summation result. So similarly in this case, your x will be, here your x is nothing but your e to the power of minus lambda by a, because in every term that is the term that is being multiplied as x squared, x cube, right? So just use that infinite sum rule and you get 1 by 1 minus e to the power minus lambda by a. Okay, so now let us simplify things if they need to be simplified a bit, that what you are left with, you have to just ultimately apply the limit, right? So in case of applying the limit, you have to be a bit careful. First of all, let us see what is the final term. So this is coming down to this. Okay. So now you can see that if you just in this term, if you plug in the limit value of lambda as lambda going to 0, then what will happen? First let us check. If we put the limit here, then lambda 0 in the denominator, lambda 0 in the numerator, and then e to the power 0 because lambda 0, and then in the denominator you get 1 minus again e to the power of 0. So it's like oh, I think e to the power minus lambda by a. Yeah, so the problem here is that here 0 times 1 in the numerator, and then in the denominator you are getting 1 minus 1. So basically you are getting a 0 by 0 term which is invalid. Okay. So in this type of case, when you reach a 0 by 0 or infinity by infinity, this kind of an invalid expression by putting a limit, then what you do to solve that is that you use L'Hospital rule, right? So use that rule. The rule is basically you have to take a derivative on both denominator and numerator and then plug in the limit. So that is the case we will do here, is basically we take the derivative with respect to lambda, because lambda is a variable in the meaning that we are getting the limit on lambda, right? So you have to take the derivative with respect to lambda. So on the this upper term you get, first take the derivative, simple derivative rule. So plus lambda to the power of minus lambda by a, then minus 1 by a, because this lambda will have a derivative and go to 1. And here on the denominator you get 0 minus e to the power minus lambda by a, then minus 1 by a. So what is the final term? Is that you get e to the power minus lambda by a. Then be careful with the sign. Here is a minus sign. So it is minus lambda by a e to the power minus lambda by a divided by, here the minus and minus will make it plus. So it is e to the power of minus lambda by a by a. Okay. So now let us try again putting the limit of lambda tends to 0. So first term is e to the power 0 minus second term is 0 times e to the power of 0. Then the denominator is e to the power of 0 by a. So what is there is that e to the power 0 is 1 minus second term is 0 divided by again e to the power 0 is 1, and then there is a 1 by a, so it is 1 by a. So the whole term is becoming a. Okay. So a is your solution. So firstly, one part you have already done with, that you have solved the left hand side limit problem, and you have got the value of the limit as a. Now what you have to do is that you just have to check the right hand side integral, and that will be easy. This is a simple integral formula, and then you just have to check that the value of that integral also comes as a, so that LHS equal to RHS can be proven. So the limit value, the integral value on the right hand side was minus infinity to plus infinity. There is a half factor to the front of it, and then the function is e to the power of minus lambda minus mod x by a dx, right? Now because our advantage is that e to the power minus mod of x by a, or whatever the function that is used in this kind of a theorem, is an even function, so its value will be the same both in the 0 to infinity and minus infinity to 0 limit. Means that even if you go to the negative values or if you go to the positive values, as long as your argument is the same, so the functional value will be the same. That's why in even function you get f of minus x equal to f of x. That means till the point you have got the argument as x, it does not matter whether you have put a plus x or minus x, the functional value will be the same. So by that advantage we can just divide, or we can break this whole minus infinity to plus infinity limit into two parts, as minus infinity to 0, then this function, and then 0 to infinity, again this function, right? And because these two are exactly equal to each other, so we can just say that it is half times 2 times, take any one of that, so 0 to infinity will be convenient, more convenient to use, then this function dx. So this is a very formal way or trick to simplify things if you have the function as an even function. So now you have only to solve 0 to infinity limit, and this is your integral. So basically you take another variable, mod x by you take as, let's say, y. Okay, then dx equal to just a dy, and this is, if x is going from 0 to infinity, so will be y, and it is e to the power of minus y a dy. So it is a, then e to the power minus y dy. If you take the integral, you will see it is e to the power of minus y, and then a minus sign here, putting the limit 0 to infinity. So it is a e to the power 0 minus e to the power of minus infinity. This is equal to a 1. E to the power minus infinity is 0, so we'll have a 0 equal to a. Alright, so we have just obtained what we expected, that our LHS is indeed equal to RHS. That means the theorem is proved to be valid for the functional value of e to the power of minus mod x by a, and the value is equal to a. Okay, so this is our one, the part 2 has been solved. Now similar way, part 3. So part 3, the function is pretty simple or short function, just you have to know the trick how to deal with it. So here the function is defined as f of x equal to, the value is 1 if your x is limited between minus a to plus a. Okay, and the value will be 0 for every other value of x, every other value of x. So this is the drill, that you have a function which shows a value of 1 only between the value of x when between minus a to plus a, and for any other value it goes to 0. Okay, so it is kind of like a step function which is showing a value of 1 between minus a and plus a. But be sure about the fact that the value of 1 is only valid for x either less than a or greater than minus. It is not at minus a or plus a, or like, what I am trying to say is that it is not that at x equal to a f of x is 1. That is not true, because x equal to a is any other value. It is not coming inside this range, right? So then at x equal to a f of x will be 0, and similarly at x equal to minus a also f of x will be 0, because here there is only this less than sign, there is no equal sign, so that you don't have to be confused about. So at those boundary points minus a and plus a, fx value will be still 0. Only in between those two ranges or those two limits, fx is equal to 1. Now first let us try our hands on LHS, the limit part. So it is limit lambda tends to 0, then lambda sum over n equal to 1 to infinity. This is f of x, right? But here let's see if our n is from 1 to infinity in the summation, but how limit from lambda tends to 0 lambda, but fx, the functional value can only show a finite non-zero value for up to a, right? So if n starts from 1, then maximum it can go up to a by lambda and not infinity. And how I am saying that? Because here we saw that f of x equal to 0 at this boundary point x equal to plus minus a. So here in this case we know that our x equal to lambda n. I forgot to put that here, so it is not x, it will be lambda n. Otherwise how can you put the limit, or how can you take the summation of n equal to from 1 to infinity? So you have to use lambda n here, otherwise it might be confusing. So here also this is not f of x, but x is replaced by lambda n as per the formula goes in the theorem. So if x equal to lambda n, then fx equal to 0 at x plus minus a. That means f of lambda n will be 0 at lambda n equal to plus minus a. Simply you just have to replace x by lambda n in all those cases. Okay. So if lambda n equal to plus minus a, then at these points what is the value of n? Find it out. It is just n equal to plus minus a by lambda. So if you write in terms of x, then the limiting points are plus a and minus a. But if you write in terms of n, which is the discrete number defining the sum, then you get at this point where n is equal to plus minus a by lambda, because you have simply replaced the value of x by lambda n. Okay, so now if n is equal to plus minus lambda, so it has both positive and negative value for both of the limits. But look at this sum, that only you get to have positive values of n, because the n value starts from 1 and goes to plus infinity. So only positive n values taken in the sum. Okay, so clearly this says, this tells you that fx gets a finite non-zero value 1 only if your, sorry, do not write it as x, rather we'll write from now on as f of lambda n. So f of lambda n gets a finite non-zero value of 1 only if n is less than a by lambda, because whenever n is equal to a by lambda, again this function goes to 0, and is equal to 0 when n is greater than a by lambda or equal to a by lambda up to infinity, any value. Okay, so I think here again I am writing this as up to infinity because in the limit you have got this up to infinity, but it is not like it is less than infinity or whatever, its range is like that. So I hope there is no confusion over here. So if that is the case, then you only get a finite value out of this sum when you get the n value from 1 to a by lambda. So that is what we are doing here. If that is the case, then simply for all this n values from 1 to a by lambda, your f of lambda n value is simply 1. So how many times the 1 can come here? The time, how many times is the value of n is being counted, the same value will be the how many times this 1 is getting summed over. So you simply take limit lambda tends to 0, and then here is a by lambda times count, so it is simply 1 into a by lambda. That much number of times 1 has been summed over, and it simply gives you this lambda and lambda cancels out, and you don't have to put the limit 0 anywhere else, so it is just a. So again here also for this function, the value of the left hand side limit has given you simply a. So just we wait for the right hand side integral. It is half minus infinity to plus infinity fx dx. Now again, because it is an even function, you can simplify it like this directly. Okay. But here also from 0 to infinity limit of x, you know that only 0 to a can have a finite value of fx, which is 1. So it is 1 time dx. And all the other values from a to infinity, the fx value is 0. So if the integrand is itself 0, so it is already going to 0. There is no point of doing this integration in the second term. And only in the first term you get this integral gives you x from 0 to a limit. So this is a minus 0 equal to again a. So this is also proven that your LHS equal to again RHS. and the value is a. So again, for both the functions you see over here, you are getting that the theorem is actually valid for both the functions. And also the first function I have solved in the last class. If some of you have missed it, you can go and check the recording from the last class. Okay, so that was basically a bit of a calculative function to do the solution, but rather this second and third one are not that lengthy or complicated. So what will be the answer for this case is that let us choose the option. I think the first case had given us the option of pi by 2a as an answer. So this is not valid because the last part is, I think, oh no, um, this is the first option that is right here, because this is pi by 2a for the first function and this is a for the second function, and for the third function it is just a again. Okay, so our correct answer for this is option number 1. Okay, great. So after we are done with this part of the solution, then we can just focus on the second problem. So again, this problem has many different parts, so we'll solve it part by part. So let us first read this out. So we are given that a gas is present where the entropy function of the gas is written as S as a function of U, V and N. So you already probably have known from the lectures that entropy is always a function of macro states. So definitely the macroscopic properties like internal energy, volume and the number of particles are the ones which comes as a functional dependence of entropy S. And you are given that this function can also be written as n times S of U by N, V by N and 1. So this is a function you have been given to have a form like this. And the first part is that you have to show that this entropy function is extensive. What do you mean by extensive? So extensive means any quantity which is actually dependent on the, let's say, which is dependent on some mass or number of particles of the system. In terms of, you can say that like volume is an extensive quantity. Like if you have two different containers, each of volume V and volume V, when they are separate they each have a volume of V, but when you merge them together, so they get a volume of total 2V. That means it has simply a linear dependence, that whenever you are merging it is increasing linearly, right? So there is a linear dependence. So you can almost say that an extensivity of a quantity can actually be checked by seeing whether they follow the linearity or not. So from math methods, you know how to check linearity of any function. Like say if your function is linear, let's say your function is x, right? So if your function is linear, then f of a times x will give you back a of f of x. Okay, so this is a trick to check linearity, of any function. That means even if you multiply the argument x by some constant a, so the answer that you give that you get back is basically that same constant a times the your old function x. So this is the check that you can also use to see whether a quantity that you have been given is extensive or not. Okay, so for this case you have to check this with this entropy value that already function is given to you. And first let me solve this and then we'll get to the next parts of the same problem. Okay, so this is our question number 2. First of all, you have been given an entropy that is function of u, v and n, and that is also provided to you that it is equal to n times function of entropy of u by n, v by n and 1. So this is given to you or defined to you. Now to check, see, entropy is actually an extensive quantity. In thermodynamics there are quantities which are extensive and intensive both. No, I don't mean that one quantity is both at the same time extensive or intensive, but I am trying to say is that there are different classes of quantities. One class is extensive and one class is intensive. For example, extensive quantities which follows as linearity behavior and actually depends on the number of particles or volume or this kind mass, this kind of quantitative description of the system. Those are examples of extensive quantities. For example, you can see volume is an extensive quantity. And then length of anywhere, if let's say our system is aware, then the length of that where will be an extensive quantity, because that is actually can be like that is a quantitative description of the system. Just okay. So as I was saying that other examples of extensive quantities will be entropy, which is S. Then there can also be internal energy U, which is also extensive. And associated with any extensive quantity, you actually get intensive quantities conjugate to that. For example, for volume, you get the intensive quantity as pressure. Okay. Same for entropy, you get intensive quantity as temperature. And again for length, you can say that the intensive quantity is maybe um, tension or force on the wear, that you can say. Let's say it is tau. So that's why they are related. If you see that in your thermodynamic expressions, you get formulas like this, that's Ts equal to U plus PV minus mu n, where all of the extensive and intensive quantity pairs are can be seen together. Like here, this T time S, which is giving you a dimension of energy in total. Here, temperature is intensive because that is not something that you can quantitatively describe. That is not actually quantitatively dependent on the system. So that is an intensive quantity. And extensive is the entropy, because that is actually dependent on these macroscopic variables like volume, mass, this kind of things. And again for pressure and volume, I told you that pressure is intensive, volume is extensive. Similar things can also be done for mu and n. Mu here is your intensive quantity, the chemical potential, and number of particles is obviously like volume or like length. This will be an extensive quantity. So just to give you an idea, this is not related to the problem as such, but these are the examples. Now as I told you that to check whether entropy is extensive, we need to check the linear scaling of S, by which I mean that you have to use something like this, that f of a times x gives you back a of f of x. Then you say that your function is linear and it is extensive. Similarly, we do something for the function. Instead of f, we now use s as our entropy function, and instead of a single argument, here there are 3 arguments, but the rule will be the same. So for all of these 3 arguments, you let's say multiply it by all of them by some constant a. Now it will be a times u, a times v, and a times n. This is your new function where the arguments has been multiplied by a constant scaling factor of a. Now you can define these new variables as u prime, v prime, and n prime. so that your u prime is just nothing but a times u, v prime is a times v, and n prime is a times n. Here a is your scaling factor which will decide your extensivity of the function. Now, as you have known that this quantity s of u v n can be written as n times s of u by n v by n 1. Just using the same thing here, you can think that is s of u prime v prime n prime can also be written as n prime comes out times s of u prime by n prime v prime by n prime comma 1. So the same thing, just instead of u, v and n, you just now use u prime, v prime and n prime. So they are the redefined forms of u, v and n, right? So you are basically doing the same thing that is already stated to you in the problem. So once you have done this, let us again put back the values of actually what are the values of these primed variables. So n prime is your a times n. Then in the argument, s of u prime is a times u divided by n prime is a times n. Then this v prime by n prime is a v by a n comma 1. So this a and a cancels out, and what you get is that simply a times n into s of u by n v by n 1. So if you remember, this is nothing but your s of u v n. So just replace it, a times s of u v n. Okay, so what you get ultimately is that s of au av an is nothing but your a times s of u v and n. So basically your scaling factor check of linearity is actually valid for this entropy function, just like I said for this simple function of f of x. So by this you can justify that indeed your entropy is extensive, because it is following the scaling relation. Once you multiply all the scale all the extensive all the macroscopic variables of that function or the system by a constant scaling factor of a, you get the entire function to be scaled by the same scaling factor of a. So that is what you have proved, that already entropy is extensive. Now after that proof is done, now check out the other parts of the problem. So yeah, then what is asked is that imagine for a certain gas the entropy function uv1 in the argument is given as u cube v square. Now find the equation of state for this gas. So for a certain gaseous system you have been given the particular form of the entropy, and you have been told that you have to get the equation of state for this gas. And after you have done that, you have also been told to find the ratio of R, that is PV by NT, in terms of what are those V by N and temperature. And then it is asked that what is the chemical potential for this gas also in terms of temperature and small v equal to V by N, and what is the energy per particle small u equal to u by n in terms of temperature and small v. So basically, to give you the gist, that first of all in the function small v, small u and 1, all these small letter is used when you are putting it per particle in terms of per particle. That means if your total internal energy is u, capital U, then once you divided it by the number of particles capital N, that means you are getting energy per particle, then you are having small e. Similarly, the total volume can be V, but when you divide V by capital N, then you are getting just the small v, which is your volume per the total particle number. Okay, and these are the arguments that are used in the entropy expression here. So by using this, you just have to find out the equation of state, and after you do that, you will eventually get the value of R, this ratio, and after that you have to express the chemical potential. So chemical potential mu and also the small u, all these values in terms of small v and temperature. Okay, so let us solve that. Let us go below the page. Okay, so this is our, let's say, part 2 of the problem number 2. Okay, so first of all, what was given, that S of small u v and 1 is equal to u q and v squared. Okay, so here small u equal to capital U by n, small v equal to capital V by n. Okay, so because you already have known the formalism that S of capital U, capital V, capital N equal to capital N times S of U by N, V by N and 1, that is equal to capital N times S of small u, small v and 1. So you see that here, if your this value is already given to you as u cube times v squared. So total S of capital U, capital V and capital N as a function is equal to capital N times u cube v squared. Okay, so if you simplify, so then you put small u as u by n, that's whole cube, then small v as v by n, its whole square. So it is basically n times capital U cube, capital V squared divided by capital N to the power of 5. So you get your total function of entropy in the actual terms of variables u, v and n is equal to u cube v squared by n to the power of 4. So up to this part we have expressed the actual formula of entropy, because before this you have been given entropy as some small u small v1. This is not the actual argument, right? You just have to get the actual expression of entropy in terms of all the actual macroscopic variables. So that we have done successfully, and after that you just have to use the first the laws of thermodynamics, that you know that TdS equal to du plus P dV minus mu dn. This is a very important formula that is used multiple places in these kind of problems. So here you get that 1 by T is equal to your del S by del U and V constant and N constant. That means when dV is 0 and dN 0, then simply your du equal to TdS. So you can just take 1 by T is equal to del S del U. Okay, so derivative with respect to U when V and N are constant. Similarly, you get when U and N are constant, that means du equal to 0 and dN equal to 0, you get P dV equal to TdS. So in that case, your P by T becomes del S in terms of partial derivative with respect to V when U and N both are fixed. So putting these in subscript like that, we mean to say is that they are fixed. They are not changing. And similarly, if you do the same thing for the last case, you put U and V as fixed, then you get minus mu by T, putting the other terms to 0, is equal to del S by del N at U and V as fixed, right? So after you have done all of that, so you just have to actually get those derivatives. So derivative with respect to U firstly. So firstly, your S of U, V and N is equal to U cube V squared by n to the power of 4. So first of all, 1 by T gives you del S del U. So you get the derivative with respect to U, it is 3U squared. Then other two are constant, so they are not a part of the derivative, so they are just remaining as constant. So it gives you 3U squared V squared by n to the power 4. Similarly, P by T, it tells you the derivative is del S by del V. So it is just simply 2 U cube V divided by other two as constant. So N and U are remaining as it is. And then again minus mu by T is equal to del S by del N. So it is First of all, let other two that are constant as it is. Then n to the power minus 4, if you take the derivative, so it is just minus 4 n to the power of minus 4 minus 1. So that means it is minus 4 u cube p squared by n to the power of 5. Okay, so if you cancel out the minus sign, you get mu by t is equal to 4 p squared u cube by n to the power of 5. So now express these as in terms of small u and small v again. So what you get is that 4 v by n whole squared into u by n whole cube. That's how you adjust the total n to the power 5. So you basically get 4 small v squared and small u cube. Okay, this is your mu by t firstly. Same things can be done also for these cases where 1 by t was expressed as this capital U, V and n terms. So we shift the variable to small u and v. So it is again u by n whole square. You divide this n to the power 4 into two parts, 2n square and n squared. So you get 3 small u square small v square is equal to 1 by t. Again your p by t is equal to 2 u by n whole cube into p by n. So that is equal to 2 small u cube small v equal to your p by t. Once that is done, so you get that you know the value of 1 by t already, and if you want to get just p or just mu, you can have that without the values of t in being involved. But other than that, you can just directly go on and know the value of pv by nt from here, because that's what you do when you get to know the equation of state for a gas. So pv by nt, what will be the value? So remember this is also the ratio r that is being defined as pv by nt, right? So you have to do nothing but put the values of p by pv, n and t in these cases. So first of all, your p is 2 small u cube times v into your t, because this is p by t, so p will be this times t. Again v remains, let's say, as it is capital V, remember this is not small v, and then n into now you have a t. Okay, so this t and this upper t cancels out, so you just get 2 small u cube small v 1 capital V by n. So you also reduce it to small v, so another small v gives you a small v squared. So this I hope is right. After that there is no mistake in the calculation. So now remember that your r has been solved here as 2 u cube v square, but in the question you had been asked that you have to solve it in terms of, I think, small v and temperature. So you are not told to retain the term small u in your final expression. So you just have to change its value so that you get everything in terms of only small v and t. So there is an easy way to do that, is basically you just take this expression, right, and here you change the u square in terms of just v and t. So in this case you have u cube over here, so you get the value of u from this expression. So your small u is equal to 1 by t into 3v squared, and you have to take a square root. So it will give you a 1 by root over 3 small v into root over of t, right? Okay. So if that is the case, then just change the variables to v squared, and then u cube you put the value that you have got for small u is 1 by root over 3 times t into v. So 1 by root over 3 times t into v whole cube. So it is 2 v squared 1 by 3 root over 3, then t to the power 3 by 2, then v cube. It is equal to 2 by 3 root over 3, 1 by v, because this v square and v cube will give you a v, into t to the power of 3 by 2. Okay, so what is our final expression is that r equal to 2 by let us check what were the options so that we can simplify our final answer in terms of that option that is already given in the choices. So let's see. Okay, so here the values are, I think, given like a minus sort of a thing, but I think there is a problem because r cannot come like this, so I think there is a printing mistake in this case. So basically we just have to express in terms of some 1 by v sort of an thing that is subtracted one from the other. So I assume that here as per my calculation here there will be another 3 by v, not just 3, otherwise the expression will not match. Okay, so let's just try what was our expression, whether we can match to that. So yeah, so ours was this 2 times, let's say we keep the 3 and t on the top, so it becomes 3t to the power of minus 3 by 2, then it is equal to simply 1 by v. So here you can just subtract 2 terms and get this 2 by v return back. So like you can get 5 by v minus 3 by v. This will give you 2 by v exactly. So this is just to match our expression with the option that is given in the choices. Okay, so this is our final option. So it would match with option number A, but there is a printing mistake. I think there is no there has to be a 3 by v and not 3 in the expression. So option number 1. So at least one part of it is done. And then what more you had been asked is, I think I remember, also this thing can also be taken as your equation of state, because ultimately your PV by NT is same as your R. So you can just say that your PV by NT equal to your this whole thing, like this in terms of small capital T and small v. So this thing can also be working like an equation of state, because ultimately your equation of state is some equation that actually connects all your macroscopic variables of the gaseous system, for example pressure, volume, number of particles and temperature together. So this can also serve as your equation of state if you just modify it like that. Now I think the last question that was asked is that you have to express your chemical potential in terms of T and again small v. Okay, so for that we have to use this final part. This mu by T was 4 small v squared small u cube. So mu by T is equal to 4 small v squared small u cube. Now again, so mu equal to T times 4 small v square, and then u cube you have to handle. You need to substitute the value of u like we had done for the previous case. So this is your value of u, 1 by root over 3 times t into v. So 1 by root over 3 times t into v whole cube. So you just get 4 t v squared 1 by 3t to the power of 3 by 2 into v cube. So mu equal to 4t, then this v squared and v cube cancels out, so this is 4t by v and 4t by v, and then you get this 3t to the power of minus 3 by 2. So simplifying it further, you get this is equal to your 4, then 3 times minus 3 by 2, then t to the power minus 3 by 2 into t gives you t to the power of just minus half, and then there is 1 by v left. So this is your final answer. So let us see with which it matches with. So yeah, so I think, yeah, this is the answer that we have gotten. So mu value exactly matches with what we have obtained, right? And again, it is also given in terms of that small u have to be presented in terms of u small v and t. That is already done. That is the expression we have been using to get mu first of all, and then also we had used it to get r. So that is the same expression, right? You got 1 by root over 3 into 1 by v, remember? So you just take it like the same thing. So we have already obtained that. So this part is also matched and this is also matched. So the final answer, the final question that was asked is that what is the value of r for a classical gas, right? So what is the value of r for a classical gas? So let us try to see what is meant by this question. Now even all of us can actually answer this question without even solving anything. So this is a pretty straightforward thing. We all know that for an ideal classical gas, PV is equal to simply NT. Here let's say our Boltzmann constant has been kept as 1. So Kv is, if it's equal to 1, so ignoring the other constant, so we just get PV equal to N times T. So that means R, that is equal to PV by NT. It is simply 1. So this is a very well-known formalism for an ideal classical gas. We don't need to do or solve anything for answering this. But still, for the sake of the calculation, since we are actually doing in terms of it in mathematical terms, so I would also like you to show that it is actually mathematically coming to be true, that this will be actually the case. How we can show that? We can use the a formula that has been used in the lecture. So you know the name, that is the secure tetrode formula of entropy. This has been um, taught in the lecture. So the formula for the ideal classical gases entropy is given by the formula is that it is S of u, v and n equal to capital N of n into log of EV divided by n AQ plus 3n by 2 then log of u by n m E A squared by 3 pi h cut squared. It is equal if that is the case, then you just have to get the PV by NT, right? So you just directly go for P by T, which is nothing but del S by del V at UN constant, that we already used in the earlier expression, this formula. So you have to take a derivative with respect to V. That means there is only this part, first term is only be valid for the derivative. So this is just log derivative will give you 1 by x, so that means it is n squared divided by e times v, then e by n squared. So this e and e cancels out, n square and n square cancels out, so this is just n by v. That means you get all the terms on one side, so you get PV equal to NT or R equal to PV by NT equal to 1. So it is proved that R value will always be 1 for an ideal classical gas. It is also known already from the basic thing that we know from thermodynamics and kinetic theory of gases, and also you can also prove this from directly using this derivative formula of P by T using the Sacco-Tetrode formula of entropy of ideal classical gas, right? So this part, second question, is also done. So second question, the option number will be first option again. Okay. Sorry. Yeah. So this will be our answer. Now, let's say third question is again based on Sacco-Tetrode formula for the entropy of ideal classical gas. So if that is the entropy, then answer the following questions: that what is the change in entropy per particle of an ideal gas that is subjected to slow expansion from initial volume V to final volume 2V, keeping temperature and number of particles fixed. That means your question is that you have to get what is the change in entropy, delta S. And not only that, delta S per number of particle, per particle. That means you have to, after you get delta S, you have to divide that by the total number of particles in, so that you get entropy change per particle. And the conditions given to you are that you have been changing a volume from V to 2V. That means the expansion. Volume change of delta V is here V to V minus V, and in this process temperature and the number of particles T and N are fixed. So dt is 0, dN is 0, only dV is not equal to 0 because that is expanding. So you have to get delta S divided by N. Now how to get that? This is simple, you just have to use the formula. That question number 3 is that your delta S is nothing but, remember that in the Sacco-Tetrode formula your volume only appear in the first term. Okay, so if you have to deal with a volume change and all other quantities like this U, which is the internal energy, that is fixed because temperature is fixed. So U is dependent on temperature. If temperature is not changing, then U will also be fixed. So this U and the number of particles is also told to be fixed. So this second quantity is not changing anyhow, so it will not contribute in your delta S. So only the first part. So that is N log of EV by NAQ. So first of all, if your delta S from going from V to 2V will be N log of EV by NAQ. In the first case, because you have gone from V to 2V, so the volume will be 2V here, minus the initial volume is E times V NAQ. So log means you just have to take a division in the argument. So it is 2EV by NAQ into NAQ by EV. So it is just N log 2. So you get delta S by N, you take N to the other side, is simply log 2. So this is your answer, that the value will be log 2 or ln 2, whatever, for the entropy change per particle. Okay, so this was a very small question, not very lengthy. So your answer is question option number 3, which is ln 2. Now comes the actual lengthy problem in this whole problem set, and the trick is that based on this one kind of problem, actually this 4, 5 and 6, all these 3 problems are based on the same formalism. So once you solve one of them, the other 2 will be just become very easy to solve, because the idea is the same for all of them, right? So first we'll definitely solve the question number 4 totally, and after we have solved that, we'll get an idea, and based on that, question number 5, answering that will be easy. We don't have to go through the all calculation again repeatedly, and question number 6 will also be followed in the same pattern. So first of all, read very carefully. So as I remember that I have already told you how to solve, but I did not actually solve it manually, the total problem, but I'll do that right now. So some of you, if you have not solved it yet, so you can just follow my steps and let me know if there is some confusion at some step. Okay, so it will be a bit lengthy, so just bear with me when I solve this. And preferably you should also take a notebook and a pen so that you can follow each step and do it by yourself. Okay, because I might make any mistake, keeping in mind that it will be a very lengthy calculation. Now see, you have been given the entropy function as a function of U and N, and there is a very general formula that is stated here, that e to the power of s as a function of U and N is expressed some kind of an integral over d theta, d phi and this whole thing, where there are several variables, with U is the total energy over here U, N is the number of indistinguishable particles. That means they are all similar to each other, they cannot be differentiated from each other, they are like quantum particles, and they are distributed among m steps. So there are m number of steps, capital M. If the particles are such that a not more than 1 can occupy a given step, then q equal to plus 1. And if there is no restriction on how many can occupy a given state, then q equal to minus 1. Now this part is already there in the lecture, that this is basically telling you that whenever you are applying the distribution for a fermion, let's say fermion has this Pauli exclusion principle, that you can only occupy a given step by one single particle. Okay, given the fact that we are not taking into account this, there is some spin to the particle, so consider it as spinless particles, not like electrons which has a spin of half. So ideally we are considering the particle is spinless. So if in that case, because it is a fermion, so only one particle is allowed at a single step to occupy. So in that case, it is standard that the q value will be plus 1 for fermions, and when there is no restriction that how many particles can be in a given step, it can be 1, it can be 2, or it can be all together. There is no restriction. So they are bosons. They are also a type of indistinguishable quantum particles, but because they do not follow Pauli's exclusion principle, so they are called bosons, and for them q value is standard to be taken as minus 1. And the epsilon j that has been used in these small parts in the expression is basically the energy for the jth level per particle. So only one particle, if you say, if that is in the jth energy level, then that energy of the particle will be epsilon j. And all this u, n, m and epsilon j have to be integers, and you have been given a special case that your epsilon j value is assigned to be only j. Your q value is plus 1, that means you are dealing with fermions, and the number of steps total is given as 4. That means there are 4 number of states on which the particles can be occupied onto. And you have been asked to find the entropy when the internal energy is u and the number of particles n equal to 2 from this equation above, and find its value from this expression, calculating from this. And also you have to use the standard, the conventional way of calculating what is the number of total arrangements possible, and then from there you have to use the Boltzmann formula of entropy, that is equal to k ln omega, or if Boltzmann constant is set to 1, then it is just ln omega. So you have to find how many number of microstates or omega is there, then you have to get the value of S. And then you have to compare these two results that they are exactly matching with each other. That once you calculate the entropy S with n equal to 2 from this formula that is given over here, calculating from this, and the other time you have to find S directly by just taking how many number of arrangements or microstates are possible there, just like we did before in the class number 1 lectures. So this kind of calculation, so then you have to compare them both, that they are actually equal or not, and then which on the following entropies is non-zero. After that you have to find that for which value of u, if the n is equal to 2 already fixed, then for which value of the total energy you get a non-zero value of the entropy. Okay, so this is your whole problem that has been given. So it has different parts, so let us follow first with the one second. Okay, so um, we first write down the integral expression, that e to the power s un, that is basically given in the problem, equal to d theta by 2 pi, then d phi by 2 pi, e to the power of I of theta u plus phi n, then product over j equal to from 1 to m 1 plus q to the power of minus I theta epsilon j plus phi raised to q. Now as has been specified that your epsilon j is j, q equal to plus 1, that means they are fermions, and total number of steps m equal to 4, and you have been asked to calculate for n equal to 2 the entropy value. So n is also given as 2. That means 2 particles arranged in 4 steps. With if j is the number of the step that you are counting, so let's say if there are 4 steps like this, so then j equal to 1, j equal to 2, j equal to 3, and j equal to 4. And your energy for each step for a single particle is also j. That means for the first step your energy will be 1 per particle, for the second step it is 2 per particle, that is 3 per particle, and 4 per particle. So these are your energies for the steps. Okay, that has already been given to you, and now we just have to manually first solve the whole expression of this, so that we can solve the integral and get the ace of entropy value from this expression, right? So to do that, first of all we just simply have to expand out this product term over here, that is product of j from 1 to m. This product you have to separate out. So e to the power of ace of u comma n equals to no, first let us just only solve the product, so that otherwise it will be messier. So first just solve the product itself. So what is the product totally? It is j from 1 to m equal to 4, then 1 plus q e to the power of minus I theta epsilon j plus phi to the power of q. So first let us put the q value of 1, then e to the power of minus I theta, epsilon j value put as j as it is mentioned in the problem, is phi, then again q value as 1, and then the product of j equal to from 1 to 4. So if that is the case, then it is 1 plus e to the power of minus I theta, first put the j value as 1, right? Then for the second term again you go 1 plus e to the power of minus I 2 theta plus phi, j value as 2, then 1 plus e to the power of minus I 3 theta plus phi, and finally 1 plus e to the power of minus I 4 theta plus phi. So let me check how much time is left. Okay, so there is still close to an hour. Yeah, so if this is our case, then this is equal to, you just have to expand out the product, right? So basically it can get a bit clumsy, but you have to put a lot of attention so that you don't miss out on any term. And I can suggest you that you can use the softwares like Mathematica can easily do the product for you, and that in that case you will have, there will be less chances of making any mistake than compared to when you use manually. But here to show you, I'll not use Mathematica. Preferably I would have used Mathematica for myself, but here if some of you might not be accustomed with Mathematica users or whatever, but for that sake I'll just calculate it manually by analytically. Okay, so just be very focused. If there is at some point is you find out some mistake in the calculation, just let me know immediately, otherwise the whole thing just gets delayed. Okay, so anyway, so that our calculation gets a bit less complicated in terms of the signs and symbols, so for that purpose we denote this e to the power of minus I theta by a variable of a, and to the power of minus I phi by a variable of, let's say, b. Okay, so a and b, so that we don't have to every time this whole exponential term we don't have to write, we just denote them by a and b. So the product just becomes simply 1 plus a times b, because it is just to the power of minus I theta into to the power of minus I phi. And the second term, it is just 1 plus a squared b, because here to the power of minus 2I theta is there, so it is a squared. And then for the third term, it is a cube b e to the power of minus 3I theta. And then for the last term, you have e to the power of 4b, right? So you just expand that out. What you get is, first let us do the first two terms. It is a squared b plus ab plus a cube b squared. Then for the second two last two product terms, you get 1 plus e to the power of 4b, so this is 4, then a cube b plus a to the power of 7b squared. So when you multiply, you get 1 plus a to the power of 4b plus a cube b plus a to the power 7b squared, plus then the second term go a squared b plus multiply this with this, so this is e to the power of 6b squared, plus with this term then e to the power of 5b squared, plus the last term is e to the power of 9b cube. Okay, so I think up to this was there was no mistake that I have made. And then go on doing the same thing with this term ab. So you see ab plus ab with this e to the power of 5 and b squared, then ab with a cube b is e to the power of 4 b squared, then with e to the power 7 b squared, it becomes e to the power 8 b cube. Then the last part is for a cube b squared, so it is a cube b squared plus a 4 and 3 is 7 b cube plus a 6 b cube plus a 10 b to the power 4. So this is your entire expansion. Okay. So once you rearrange your terms so that they look a bit more tidy, so you just take common of b square, b cube, all these terms, so that what we are trying to do is that we are trying to arrange the terms so that you can have powers of b on each terms. Like first term is 1, that means b to the power 0, then you have b, which is b to the power 1, multiplied by some coefficient which we will get, and then plus again b squared multiplied by some coefficient, then b cube with some coefficient, like this. So basically it is some sort of a series, power series of b with some particular coefficient associated with each term. So in this way our problem will be simplified. So first of all, find out how many b terms are there. So it is this term, then this and yeah, I think these are the 4. So it is a4 plus a cube plus a squared plus a. Okay, b is done. Then for b square you do the same thing. So here are your b square. So let me use a different color here. So this is b square, this is b square, this is b square, b square, b square, b square. Okay, so here you get the coefficient as a7 plus here 2a5 we have obtained. So sorry, there was previously a to the power 6, then 2a5 plus 1 a4 plus 1 a cube, right? Then you do the same thing for b cube. So again let me mark it by blue here so that there is no mix match. So this is b cube, b cube, b cube, b cube, 4 terms. So you see b cube has e to the power 9 plus e to the power 8 plus e to the power 7 plus e to the power 6. Okay. Now finally you have b to the power of 4. So let me use right here. Yeah, so where at b to the power 4, we see that there is only one term in b to the power 4, right? So this is just a single term. So this is b to the power 4 times a to the power of 10. Okay. So we have very nicely arranged our terms so that there is no mix match or confusion over here now. You have quantities with coefficients in with b squared, b cube and b to the power 4. Now this part is done. So basically this is a summation of the terms, like you can say this is a n comma m, where b to the power of n and a to the power of n and summation of n comma n. This series is in general expression of this total sum. Why I can be able to write it like this? Because let's see that there are terms as b to the power of n. So these are b's power of b, where they can have different values of n, right? Like here there is b, then b to the power 1, b squared, b cube and b4. Similarly, there are also power of a as a to the power n. So also sum of m is also present, because you can have these summation values on a also, where you have all these powers of a from a to a squared to a cube, even up to, I think there was a to the power 8 or 9 also, up to a to the power 9 I think there is present. Oh sorry, a to the power 10 is also there. So up to these powers are also there, and each of them has a certain coefficient associated to that, and that coefficient we denote by some capital A subscript n comma m, because for a particular value of b to the power of n and a to the power of m there is a certain coefficient, and that the whole thing, if you sum that up, that makes your whole expansion of this summation term, right? So this part we have been able to simplify, right? Now after we have done that successfully, we'll go back to our integral, because we need to solve that integral so that we get our entropy, right? So first of all, one thing will come as useful in our integral solution is that we have to use the definition of delta function, chronicle delta. How is that? It is that d theta by 2 pi e to the power of I u theta minus n theta is equal to delta of u comma, let's say why I'm using u and n, let's say use simpler terms so that there is no confusion. Let's say use x and y instead. So this will be like chronicle delta of x comma y, so that this value is 1 when x equal to y, and it is 0 for all x not equal to y. Okay, so this is our definition of chronicle delta, right? Now because remember that our total integral had a expression like this, that 0 to 2 pi d theta, I think by 2 pi also was there, d theta by 2 pi, and then 0 to 2 pi d phi by 2 pi, and you had to the power of I u theta plus n phi into this whole product term, right? J equal to from 1 to 4, this product term. Now remember, this product term you have already solved, and the general value we have gotten as a summation, like this summation, right? A n m b to the power of n e to the power of m. So we can always replace that sum on this product whole expansion, right? So you do that. This is 0 to 2 pi d theta by 2 pi, 0 to 2 pi d phi by 2 pi with the power of I u theta plus n phi into this thing. Just as I said, this is just the expansion of that summation as we have obtained, e to the power of n, e to the power m. Okay, now after that, after this point, because to see that we have to use that Kronecker delta expression here. So how will we use that? So first of all, remember that all this while we are assigning this b. Remember what was b actually? Our b was e to the power of minus I phi and a was e to the power of minus I theta. So it's time to take them back, that b equal to the power of minus I phi and a equal to the power of minus I theta. Now we have to return back to the exponential so that we can have this whole Kronecker delta expression to simplify our solution. So write it like I u theta plus n phi, and then just a sec. Okay, so yeah, so let us just now put the values of b and a. Summation over m comma n. Then b to the power n is just e to the power of minus I n phi, and e to the power of m is e to the power of minus I m theta. So after this, you have to very cleverly separate terms out so that you can have Kronecker delta expression like that. How to do that? So first of all, let us go with this phi term, right? So let us first take out this m comma n, am n aside, and also keep the theta term also aside, so that minus I m theta is separate, and also this e to the power of I capital U theta is also separated. Only the phi terms we are interested in. It is d phi by 2 pi, phi from 0 to 2 pi. Then we take out these two terms, e to the power of I n phi and e to the power of minus I small n phi. So we'll write e to the power of I capital N phi minus small n phi, and this is our whole expression that we have obtained, and this is nothing but our Kronecker delta definition. So it is Kronecker delta of capital N comma small n, because here there is, in the subtraction, there is small n and capital N. Okay, so once that is done, you know how Kronecker delta works, that if you, let's say, have summation over small n already, and you have a Kronecker delta sitting here in one subscript is small n, so you can replace wherever in the functional form you have a small n quantity, you can replace that by capital N now, right? So you can see where there is small n present in the function, everywhere else you can find out that it is only present in the a m comma n term, that here there is a small n and nothing else there is present. So you can just absorb the summation over n into that Kronecker delta adjustment. So basically what you do is that you do this thing, summation over m comma n, a m comma n delta capital N comma n. So sum over n is everything that is being absorbed. So you come out with sum over small m remains as it is, because there is no Kronecker delta action that is doing, that we are doing on that. Just small over sum over n will be absorbed, like this part coming out. Okay, so this is a standard Kronecker delta thing that I think you all know, so I'll not elaborate. And after that is done, so basically you just replace here m, now a m comma capital N here, and also you do the same thing with theta term also, where I theta capital U minus small m. So just see, if you take this thing to the left, you can get again a Kronecker delta expression, but this time in terms of theta variable, but the expression is same, right? So you can redefine another Kronecker delta term here. So it is just m comma n, and then it is delta of capital U comma small m. Again the same thing, sum over m will be absorbed with the Kronecker delta, and with the coefficient the m value will be now replaced with capital U. So it is A with the subscript capital U comma capital N. So remember, these are the coefficient of b to the power of capital N and e to the power of u, because in this series expansion term the summation term went like this, where this a small m comma small n were basically the coefficient adjacent to b to the power of n in power and e to the power of m in power. So here, because they are capital U and capital N, so the m is now capital U, so your power of a will be capital U and the power of n b will be capital N. Otherwise the whole thing is the same, just the variable has been changed. They are dummy variables anyway, so they have been changed. So now remember that we have solved the integral here. So e to the power of s u comma n is now the integral value of solution is coefficient with b to the power of n and e to the power of u. Now let us look back and remember the problem that we had been told to actually find out what was the value. Yeah, let's just go back to the problem for once. We are asked that we have to get s of u n comma 2, and so that the value we can get, and then also solve it from microstate count. After that we have to find out all these values of u 4, 2, 3, 4, 5 and 6. 4 values of u are given for n equal to 2, and you have to know what is the non-zero value of the entropy out of that 4 options. Okay, so let us go back. Just you now have to match the coefficients and you will get the answer. First of all, they had asked us to get s of u n equal to 2. That means, first of all, this tells you that it is u comma n equal to 2 is simply nothing but the coefficient with n equal to 2. That means you have to get the coefficient of n is the power of b, right? So b to the power of n. That means you have to get the coefficient of b squared, all the coefficient of b squared, because the value of a is not specified out. It can be any value of u, so it is a to the power u. U value can be varied, but b square has been fixed to u. So you have to see the coefficients of b squared. So you get, where we had done that is here. So these are all the cases. Okay. Yeah. Our values will be a to the power 7 plus a to the power 6 plus 2 a to the power 5 plus a to the power 4 plus a to the power 3. Now all of them has a coefficient. We have to look for the coefficient, not these variables, because these are the a to the power of u variables, right? But let's say the coefficient that you can define for u comma n, where u value is, let's say, 7 and n value is 2. Now when b is equal to 2, so you can see that they have specified n equal to 2 over here. Now all of these different choices of u, where u is the power of a here, so we can have u equal to 7 for the first term, where a to the power 7 is there, and you see that a to the power 7 times b square, this term has a coefficient of 1. That means a u equal to 7 and n equal to 2 is nothing but 1. By the same rule, if you want to get a u equal to 6 and n equal to 2, it is again 1. This term, coefficient 1. Same goes for u equal to 4 and u equal to 3. Only for u equal to 5, where there is a 2 a to the power 5 term, so there the coefficient is 2. Only there you get that a u equal to 5 and n equal to 2, the coefficient value is 2, right? So this is the case that, let's say our is equal to 5 equal to 2 e to the power of that is equal to a 5 comma 2, that is 2. So if your s is that, e to the power s is that, then s equal to 5, n equal to 2 is simply ln of 2. Okay. Now this you have calculated using the whole integral expression. Now you can have the check for yourself that whether this also has been asked in the question, that conventionally just count the number of microstates for this special case and see whether it matches with the calculation result, right? So what is the specified case over here is that you have been given 4 steps that were specified already with energy of 1, 2, 3 and 4 per particle on each step, and these are fermions, that means one particle on each step, 1 or 0, not more than that, and you have been given only 2 particles because n equal to 2. So to have total energy as 5 out of 2 particles on these 4 steps, how you should arrange? So you can either put one particle here and one particle here, 4 and 1, so that 4 plus 1 equal to total energy is 5. Remember, these are indistinguishable particles, so it does not matter whether you which particle you put on which level, so they are equivalent. So this is one choice, and another choice is that you put, so these are 1, 2, 3 and 4 in energy, so you put one in the third level and other in the second level. So here also the total energy is 3 plus 2 equal to 5. So no other possibilities are there. If you check that in all the other cases you cannot get the total energy as 5. So with this condition specified, you know that there are only 2 microstates possible, or omega equal to 2. That means S equal to ln omega equal to ln 2. So you can see that how conveniently this conventional calculation actually matches with this total numerical analytical calculation that we had done from the formula, that actually for this special case it is entropy is ln of 2. Now you are also asked that which one of the cases is giving you a non-zero entropy. So clearly for n equal to 2, only for e equal to 5 case the entropy value is non-zero because it is ln 2, which value is not 0. For all the other cases we saw that the coefficients value are all 1. That means for all a7, a6, a4 and a3. So 3, 4, 6 and 7, all these 4 options, that means equal to 3 or equal to 4 or equal to 6 or equal to 7, all these 4 cases, if your total number of particles is fixed at 2, then the coefficient value of u comma n is 1. That means e to the power of s u comma n equal to 1, and that means s u comma n is just ln 1, which value is 0. That means for all these cases the entropy value is 0 except for this case when the total energy u equal to 5. So the option for which entropy is non-zero is just e equal to 5 and n equal to 2. Okay, so you can also check take one of these examples and actually check for yourself whether this is actually true from microstate configuration as well. Let's say you have 1, 2, 3 and 4 level and you have 2 particles, so that you can have the total energy of 6. So how can you do that? How many ways? So you can see that there is only one way. One particle have to do at 4 and other at 2, so that 4 plus 2 equal to total energy of 6. There are no other possibilities existing to have this total energy out of 2 particles. So clearly omega is equal to 1 and is equal to ln 1, which is 0. Similar thing you can check for yourselves for this and this, and you will find that exactly they are consistent and that our mathematical calculation actually is valid. It is actually giving us the right answers that we can also check from the counting of the microstates for this special case. Okay, so this is a particular case of problem that we have already successfully solved. So once that is solved, then the other two are very easy because they are on the same line almost. So let us just read that and get the answer to that. So in the second problem, you are given the same formula of entropy, and let us see where there is a difference. That here your again q equal to -1. Remember that for the last problem you had q equal to +1, right? That means they were fermions, but we know q equal to -1 is for bosons. That means there is no restriction on how many particles can sit at a level, that as it is conditioned on the problem itself, that you can have one particle or more than one, whichever amount of particle you want to place at one level you can do that. There is no restriction, and the number of steps remains the same as 4. So in that configuration you have been told to you have been asked to actually get these and these values. So a particular value of n is given as 2 and u value is varied from 4, 6 and 7, and you have to get the entropy. So now if you just go back to our solution, I will not solve the entire derivation for you once again, just changing the value of q, because it is the same problem, right? Just the q value has been changed. So I'll just tell you where the change has been done, and you can just check for yourself so that you can also have a habit of how this thing is done. So here where we had put q equal to -1, so we have to put q equal to +1 for problem number 5. So how does it change this total system is that here it is 1 minus instead of 1 plus, and then it is the to the power of this thing is to the power of -1. So that when you take out the total product, so you have to adjust accordingly. All these terms will not have a similar thing. There will be change of the coefficients, and based on that again you have to find some coefficient of a n comma m, where all these things the n value has been fixed to capital N equal to 2, number of particles is 2. So your B will be already always at B squared, and you have to find out, I think your U value was specified as 3, 4, 6 and 7, I think. So let me check, 4, 6 and 7, yeah. That means your A value will have a power of a to the power 4, a to the power 6 and a to the power 7. So you need to find out the coefficient with a to the power 4 b squared, a to the power 6 b squared and a to the power of 7 b squared. And after that will give you the e to the power of this thing's value, and you just have to take the ln of that value and you will get actually the what is the value of s of a particular u and n, right? So I think this thing is pretty similar. I don't need to calculate the whole thing for you, but we can check what is the answer from the given options just by our usual microstate calculation, right? So problem number 5, first of all, s of u equal to 6 they had given, n equal to 2, with the particles are bosons now. So that means you have 4 steps, 1, 2, 3, 4 are the energy levels and the value and the level of the step, and you have 2 particles, so that the total energy is 6. How many ways you can do that? So you can do it like 4 and 2. So and also because you have one more possibility, because now we can put both particles on the same level, unlike the fermionic case. So this is 2, 3 and 4. So if you put both the particles on the level 3, so you get the total energy as 3 into 2 equal to 6 also. So here 4 plus 2 equal to 6, and here 3 plus 3 equal to 6. So there are 2 possibilities. So omega is 2, that means your s for u equal to 6 and n equal to 2 is nothing but ln of 2. Similarly, check for the second case, u equal to now 4 and n equal to 2. So again draw the 4 levels. How to get total energy of 4? By 2 particles. So you can get 2 on the same 2 level. So 2 plus 2 equal to 4. Or you can get 3 and 1. 1, 2, 3, 4. So you can get 1 at 3, 1 at 1. So again 3 plus 1 equal to 4. So omega is equal to 2, and here s value is ln 2 again. And for the third case, when your s value is for e equal to 7 and n equal to 2, so how to calculate that? Just draw the levels. Then you can put 4 plus 3, so that it's 7. And now no way there is another possibility to present the total value as 7. So here omega is equal to 1 and s equal to just ln of 1, which is 0. So our answer will be matching with ln 2 and 0. Whichever option it matches with, that is our answer. Okay. So let's check the question again. Yeah. So our answer will be option number 1. Then the last question is pretty similar. You will see that here the same formula is again put again, and the q value is here +1. That means just like the case that we had for question number 5. And also the other parameters are same, that is epsilon j equal to j, number of steps equal to 4. The only change they have made is that n equal to now 5. You have now 5 particles and you have to calculate the entropy for 5 particles. Okay. So for that case, so either you can choose to do it the mathematically by the exact same solution I have used for question number 5. But before that, let me just know the answer directly by the microstate configuration. And then we can also check whether that is right or not. So this is our question number 6. Now this is exactly similar to question number 4, where Q value is plus 1. That means there is a restriction that only one particle at most can be at a level. That means they are fermions. Okay. So we have been asked to get e to the power of s u n equal to 5 with 4 number of levels. So this is 1, 2, 3 and 4 as energies of each level per particle, and you have to rearrange the particles which are fermions, that are 5 in number. So you can see that because they are fermions, if you at maximum put one particle per level, still you are short on the number of levels. That means you have still one particle left, but you have no level to put that particle, one extra. Okay. That means there is no configuration possible if they are fermionic particles. There is no configuration possible where you can rearrange 5 particles into these 4 levels. So that means you cannot have a configuration. That means your number of microstate, I think, will be 0 here. Okay, so that is there is no count rearrangement way of a rearrangement that is possible. And due to that, your S is k ln of 0. You know, ln function goes something like this, that at x equal to 1, ln value is 0, and x at 0, ln value almost diverges to minus infinity. So it is a function almost goes to minus infinity. So if you take in e to the power of s u comma n equal to 5, it is just e to the power of minus infinity, which goes to 0. That means your answer here will be 0. Now this thing is given. We can also check the same thing by your mathematical formulation by checking the coefficient value. You have to do n equal to 5. That means the coefficient with b to the power of 5. And a value can be any coefficient of a to the power of u. Okay, so let us check what was there for b to the power 5 in the product. So you see that there is no existing b to the power 5 term at all in that product, right? So this coefficient of b to the power 5 times some a to the power u will be obviously 0. That means again your e to the power of s will be, your coefficient value is 0. So directly you can get that the answer is 0. So this is for question number 6, I think. So with this we are done with all the assignment problems that are given last week. So this is our question solution is 0. So I hope up to this part everything is clear for you. So so if that is done, then let me check what is the time remaining, so that I will just there is not much time left, maybe 10-15 minutes. So I'll just tell you some, I think this week's assignments are not some sort of a like I'll not say calculation, as calculations are not there, but mostly it is based on the lecture material that has been given to you. So it is not something that you have to apply some tricks and then solve. It is just simple derivations that you have just to be patient and solved step by step. So still just let me open this week's this problem set. So I hope you can see assignment number 3, right? So basically, the first two problems are based on Legendre transformation. So once you know the idea of Legendre transformation, then I hope you can solve both of them very easily. And the first one is already well known. Lagrangian function, if you Legendre transform it, it will already give you a Hamiltonian, right? Because that is well known from classical mechanics, that for a Lagrangian, the Legendre transform of a Lagrangian is always a classical Hamiltonian. So first, let me just, I forgot to take these questions out. So let me do it now. And then, okay, let's say for the first three questions, we try to solve, not solve exactly, but try to see what are given. So this is our week 3 assignment. So I'll just discuss very briefly so that you can know the type at least. Okay. So first of all, just like I said, that the first two questions are nothing but the idea of Legendre transformation. So it is very simple. Actually, you can find it out from any math physics book. But for you, I'll just give you the basic thing of Legendre transformation. Legendre transform. So the definition is like that if you have a function, let's say f of x. So yet for simplicity we are choosing a single variable function, only a function of x. For more complicated function there can be multiple variables like x, y, z, there can be many other. But for simplicity, to actually follow the rule, we take a single variable function f of x. And you want to Legendre transform that function to some different function of f star, where the argument is no more x, but the argument has now been changed to df by dx. So that means this new transformed function f star has a dependence on not x but the derivative of f with respect to x. Okay, and how that is defined is that this is the idea of Legendre transform, that to get f star as a function of df dx, you just have to take f x, then minus the variable that is being changed, that x is changed to df dx, right? So you have to take that independent variable x, then multiply it with the derivative df dx. So this is your definition of Legendre transform. Or it can also have a negative sign flip. That means instead of this you can also get a function which looks like this. Anyway, but the terms should be like first the original function, and then you have to have the independent original variable x times the original function getting a derivative with respect to that original independent variable. That in a whole gives you the transformed function. Okay. So for simplicity, you can define this df dx as a new variable so that it is less, it is more tidy. So if y is equal to d or df dx, then your new Legendre transformed function is f star of y, and your old function on which you are doing the Legendre transform is f of x. So the by definition f star y will be f of x minus x times df dx minus means minus x times y, or it can also be xy minus f of x. So this is your Legendre transform thing, and remember that here you are changing variable from x to y. So you are basically in the transformation, you are basically changing the functional dependence variable, changing the independent variable from x to y with the condition that y, the new variable, is equal to the derivative of that first function with respect to the original independent variable. Okay, so this is the basic idea. By doing so, you can easily find out how this Lagrangian in classical mechanics, which is L as a function of q and q dot, where q is the positional coordinates, q dot is the velocity coordinates. Okay, and you know that momentum coordinates are defined by p. So there is a formalism in classical mechanics that p equal to del q by del q dot. That means a derivative of Lagrangian with respect to the velocity is your classical momentum. if that is the case, and you need to get the Legendre transform of Lagrangian, so that you want to change the variable of q dot to some other variable, let's say p. So how to do that is just the simple, again the same thing, is that you need to we will use this reverse formula here, that x df dx minus f of x. So that means the variable you need to change is x. Here the x variable is q dot, because you are changing the variable q dot to p. That means your x is q dot, and now the new variable y is p. With the condition that is satisfied is that y equal to del f del x. So here your p equal to satisfied as del l del q dot, right? So you can apply that easily. So this is your x y minus fx will be p times q dot minus l, your original function. And because there are multiple number of variables like that, so it is generally defined as a index of I, so that there is a summation over I, pi times qi dot minus l as a function of qi comma qi dot. So this is your whole thing, where this is your Legendre transformed of the Lagrangian, which is nothing but your classical Hamiltonian qi comma pi. So the answer is already shown to you, that your classical Hamiltonian is the Legendre transform of classical Lagrangian. Now the second problem I will not totally solve, but it is exactly same, in the same way we can do very in a very brief manner. Here you have been given that you have to do the Legendre transform of the entropy function. Okay, entropy. So entropy is generally a function of all the independent coordinates, but like this, in this case, let's say it is also versus the total number of particles. That means your independent variable that needs to be changed here is n. So basically your x is n here, and you have to have a Legendre transform of entropy to some other variable, so that it is ds by dn, right? So just have to do the same thing, just do it by yourself, just use the general definition of Legendre transform, and by simplifying you will get that you will reach one of these expressions. Okay, so I'll not solve it any further. Then to give you the hint on the third question, again it is not very difficult. There is a energy per particle small u, that means capital U by capital is given to you in terms of temperature, and you have been asked to get the formula for pressure versus temperature and density of particles. That means you have to get pressure in terms of the temperature T and the density of particles, that means n by v equal to rho. So in terms of these two terms you have to express your pressure. So how to do that is, I think you are familiar with the whole equation of state, right? So you know that how for this is remember, this is a quantum gas of non-relativistic particles. So you know what is the equation of state for quantum gases, given that they are non-relativistic. So by the same thing, you know that the equation of state is just PV is equal to 2U by 3, where U is the total internal energy. So this is enough of hint to give solve this problem for you, that you just have to use this value of small u in this case, and you just directly get capital P, the pressure, as a function of these other terms, right? So this is your hint. And then the other problems, let me again see what were the other problems. Okay, so there are these 4, 5 and 6 and 7. So first of all, these 4, 5 and 6, all these three are basically not something in terms of mathematics, but it is just derivational sort of things. So you just have to follow the lecture notes or find some online lecture notes or some book. They just have written down the steps exactly. You just have to do the inner steps calculations to get in between the steps. So like in the case of this question number 4, It is that find the expression for entropy of ideal Fermi gas at low temperature to leading order in temperature. So this is entropy at the low temperature limit for the ideal Fermi gas. You can get the exact same topic in any standard textbook of StatMech, and you can get the derivation done by yourself. You just have to use the limit of t tends to 0 for this case. And similarly for question number 5 also, this is for non-relativistic fermions again, that means Fermi gas, and in 3D, and here you have to use a high temperature limit, and up to leading order contribution you have to get the entropy. So these are actually basically, if you get done one of them, you can do all the others, but they are basically very long derivations, pages after pages will be needed for that. But actually this is a textbook problem, so I'll not solve this for you here because this is not something of a solution, as I told you. But definitely I'll get the derivation done in our upcoming class. And then for the last problem I'll give you a hint, because this is actually a solution kind of a problem. This is a problem about the Bose-Einstein condensate, that what is the temperature at which the condensate fraction becomes zero point 0.5 for a non-relativistic Bose gas in 3 dimensions, and the options are given all in terms of Tc. So the basic idea here I will tell you that this is a question number, I think 7, right? So question number 7 is actually a sum where you can directly use the formula of Bose-Einstein condensate, and also you can get to know the physical meaning of that alongside the problem. So Bose-Einstein condensate is basically collection of particles which are bosons at a very low temperature, below some critical temperature like T less than Tc, where all these bosonic particles, they lose their independent identity, and they all behaves in a collective manner like a single quantum state, which is so large that you can even see it with naked eye. So basically Bose-Einstein condensate is that a large number of particles which are bosonic in nature follows a Bose-Einstein distribution. So below a certain critical temperature of Tc, when the temperature is so low, in the low limit, then they all combine together and behave collectively. That is your Bose-Einstein condensate. It is like a single quantum system instead of individual quantum particles. Behave collectively. So if you follow the lecture notes and the textbook things, so you can get that what is the number of particles that are present, particles at the ground state, that is E equal to 0 state, in a Bose-Einstein condensate system. That is given by n subscript 0, that is n naught. Okay, so if your n naught is that, then the basic and total number of particles is capital N. So the fraction goes like n naught by n equal to 1 minus T by Tc to the power of 3 by 2. So this is a straightforward formula. You can just use this fractional value as put as 0.5, and you will get what is the value of T in terms of Tc. So there we'll get directly the answer to that. But actually it will be nice if you just get the solution of n naught by n done, because ultimately you are because you are learning the course, you have to also get to the not only problem solving but in terms of the physical aspects of it. So once we do the derivation in the next class, I'll also tell you what is a physical understanding of that why are you like calculating this fraction of particles at E equal to 0 state, how are they sitting at E equal to 0 state, and what is the physical significance of all of that. But for now, this is the direct formula that you can use to get to the value of n naught by n, plug in at 0.5, and you can get T in terms of Tc from that. So I think that will be all for this tutorial session. Time is also over. So if from these lecture problems, if you have some doubts, you can ask me right away, or we'll meet in the next class. Okay.
Madam,
Yeah.
in question number 5, are the particles are distinguishable or not distinguishable?
One second. Question number 5.
Fine.
Yeah, particles are indistinguishable because you see they are fermions. So fermions means quantum particles, so indistinguishable.
Okay.
Yeah. So basically, I just as I told you that you will find the same kind of a problem in any basic textbook that is probably also referred to in the lectures. So there you just have to in the two problems there are two different temperature limits are used. One is for problem number 4 there is this low temperature limit, and problem number 5 is for high temperature limit. And problem number 6 is also the same as 5, but only now you have to also take another contribution to t. That means the powers of t up to leading order you had to choose up to leading order in 5, and then up to in 6 you had to choose the next leading order contribution. So it is basically nothing more than a very rigorous derivation, nothing other than that. So just try it by yourselves, follow the book steps, the equations, and get the in between steps done by yourselves in the derivation, and hopefully you can get to the ultimate answer. Okay, so if I hope there are no more doubts. So basically we can finish today's session, and I'll meet you in the
Thank you,
next.
thank you. Very nice.
Oh, thank you, madam. Today it was very nice. You
Very
always,
nice lecture.
yeah. Thank you so much, ma'am.
Yeah, sure, welcome. Okay, so you don't have any doubts now?
No, no, ma'am, not now.
Okay. Okay, all right. So then we will meet in the next class. So, okay. Bye then.
Thank you.